after they get it on the day that we do it, they never recognize it. That's what I've noticed. So, here are two things that I tend to notice that help me recognize it in the future. One thing that's big that helps me recognize it is that there's two variables. Did you guys pick that up? Is that the variable that's like in the integral and the variable that is like the bounds of the integral have one variable and then the variable in the integral are different. And then the other part is that if this is f of x, they're telling you to find f prime of x. Those are like the two things that I pick up that help me recognize that we're using the second fundamental theorem. And it's common. It shows up all the stinking time. So it's good to notice it. And then this is something, definitely flag this assignment because it should be on your cheat sheet, multiple examples that are good, because it's going to show up on problem sets a lot in the future because it's such a main idea that students tend to like be confused about. So were there any problems on here, like first page 1 through 17? Do we need to talk about it all? 1 through 17, we're okay? All right, how did we feel? The graph ones were really getting at the conceptual part of that the integral is talking about the area under the curve. That's what the graph ones were getting at, yeah. So which one should we talk about? 18? Okay. Yeah. It was a lot. Okay. So here it says that g of x equals the integral from 0 to x of f of x or f of t dt. So this means that if you want to find, let's say if you want to find g of 0, then that would be the interval from 0 to 0. Does that make sense? The interval from 0 to 0. So the interval from 0 to 0, that's going to be no output. There's no area when your slice there is nothing, right? Your slice is nothing, so that means that my output is 0. Then if I'm plugging in 1, my area from 0 to 1, my area right there is a -1. Does that make sense? Because it's beneath the x-axis. So any area that's below the x-axis is negative. Any area that's above the x-axis is positive. So my area from 0 to 1 is a -1, so I put a -1 down there. Then if I look at my area from 0 to 2, from 0 to 2, that's a -2. From 0 to 3, that's a -3. So that's where I got the 0, -1, -2, -3. Now my area from 0 to 4, this is where it starts to get a little bit more interesting. Now I got a half in there, so -3.5. Everyone see where I'm getting the numbers in the table from? Okay. Now when I got to 5, we started getting our negatives. Now we're adding a positive back in there. So I got -1, 2, 3, 3.5. But plus another half gives me -3. So now I'm taking all this negative area and I'm starting to add positive areas back into it. Does that make sense? Okay. For 6, I took the area of 3 and I added 1.5 back to it. See this positive area, 1.5? So I took -3.5 and I added 1, 2. And that's where -1.5 came in there. Because it had all this negative area first. Because it says it's the area. So if I want g of 6, then that's the area from 0 to 6. G of 6 is the area from 0 to 6. And the area from 0 to 6 is all these negatives plus some positive. So overall, that's still going to be a negative area. It's just a little bit less negative than it used to be. And then here you can see this right here is me doing the calculations for the area from 6 to 7. So I took this number and I added the little bit of positive that I got to it, and that's where I started to get a positive answer now. So that's how I calculated all those numbers. Does that make sense?
How do you know if it's applying to like the slope, if it's applying to something else with derivative, and then the now area under the curve, is that also derivative?
So this is just being careful to really understand all the relationships going on. So I know because it said g of x equals this, then g of x, this x and this x are the same thing. See this x right here and that x right there? I know that if I plug a number in right here, it's the same number as goes right there. And I know that this notation means area under the curve. Well, I just know this notation means area under the curve. That's what integration sign means. It means the area under the curve. So that's why I'm reading it like that. Does that make sense?
Yeah, I'm still confused on the g prime of x.
Well, we haven't even gotten there yet. So I haven't even touched g prime of x. So right now I'm just reading, this is how you plug numbers in. And this is how you filled in this table. Does that make sense? Okay. So now if we want to know what g prime of x, this is where we can use the second fundamental theorem of calculus. So if I want to use g prime of x, this is where I say, okay, now I'm doing a derivative here, which is part of the second fundamental theorem, and now I'm using the fact that there's two different variables here. So this is where I say, I'm going to show all my work. So the second fundamental theorem says you plug this in, and then you multiply it by the derivative. So I'm going to do g prime of x is f of x times 1 minus f of 0 times 0, because the derivative of a number is just 0. Does that make sense? So this is me doing the second fundamental theorem of calculus. And then because f of 0 times 0 is just nothing, I can get rid of that. And because f of x times 1 is just f of x, my conclusion now is that g prime of x is the same as f of x. So what I can do with this information is I can say that these outputs, these actual, that f of, so it says the function in the figure is f, so f of 1 is negative 1. F of 3 is negative 1. F of 6 is 2. F of 10 is 0. So now I can look at all those and I can say, hey, those are actually slopes. That g of 1 is negative 1. That g of 3 is negative 1. That g of 6 is 2. That g of 10 is 0. I can now read it and say, oh, this has g as a negative, g prime is negative, and then g prime is positive. So if I want to know where g prime switches from negative to positive, it does that at 4. Which tells me if it switches from negative to positive at 4, what does that tell me about the function g? It's a minimum. Does that make sense? So that's the benefit of knowing that f of x represents g prime of x, because now I can tell you something about g. That's why we care. Does that make sense? So this is the reason that we like the second fundamental theorem, because it can help us make this extension. This is a common FRQ. This right here, taking something like this, doing this, and arriving at this conclusion, and being able to use it to read a graph and find maximums and minimums and things like that. This is a common. A table. integration. The table was just area under a curve. So you can do this exact same thing you could do in 19 and 20 as well. So in 19 used what we learned last time too, right? It said if g of 0 is 3, what's the value of g of 4? So this one is asking you just to use integration. So g of 0 is 3, so we start with 3 plus, and then we're plugging in 4 for x. So we're saying if we want this y coordinate, we're going to have to read the graph and find the area under the curve to do it. So we're going to start with 3 plus the integral from 0 to 4. And then I'm going to use the area under the curve to help me find that y coordinate. So if I look at the area under the curve from 0 to 4, I can see that the area under the curve from 0 to 4, this is an area of 5, and then this is an area of -1. So 5 minus 1, so that's an area of 4. So 3 plus 4 is 7. But it works the same. It's the same idea, but it's really just the area under the curve. Yeah, this is just me showing my work. My positive area plus my negative area, 5 minus 1. So 3 for my initial value plus the area under the curve, 3 plus 4 is 7. So my output is 7. And then when it says what x value does g have a minimum, now all of a sudden I have to use the second fundamental theorem. So now I have to go back over here and I have to say, okay, g prime of x is f of x times 1 minus f of 0 times 0. And then this we can get rid of. So, all right, g prime of x equals f of x. Okay, so second fundamental theorem told me I don't need to talk about the area under the curve anymore. Now I can say, okay, the curve itself represents g prime. So if they want to know where g has a minimum, I just need to look to see where the graph is switching from negative values to positive values. Okay, and I can consider the endpoints as well. So I can look at relative minimums and I can look at absolute minimums. So if I look for relative minimums, I'm going to see that at 5.5. Does that make sense? 5.5. And then if I look for absolute minimums, I'm going to consider 7 and I'm going to consider 0. So remember the extreme value theorem says that because it just says where does it have a minimum, it doesn't clarify if they're talking about an absolute minimum versus a relative minimum, so we have to take both into consideration. Does that make sense? Since they didn't say relative or absolute. So a lot of us, whenever we read the word minimum, we just assume they're talking about relative, but that's not necessarily the case. So absolute minimum, we always look at the relative. So we look at the ones we're used to looking for, and then we also consider the endpoints. And when we consider the endpoints, we think about the y-coordinates. And the y-coordinates we're going to find just by taking this right here and doing that 3 plus. Does that make sense? This is how we're finding. So 7 is the y-coordinate, it's just the output. So if I wanted to know the y-coordinate at 0, g of 0 is actually not 0, it's 3. Because it just says if g of 0 is 3. So part A said if g of 0 is 3, but based on this right here, if we use g of x equals this, then plugging 0 in there, it should be from 0 to 0. Does that make sense? So for part A, they said if it happened to be 3, then what would this be? But if we assume that this information was only true for part A, if it's only true for part A and the rest of the time we're assuming that's not true, then G of 0 would equal 0. So the difference is if they wanted you to use this information for all of the problems, they would put it in this part right here instead of in part A. Does that make sense? Okay. Although I could see them, and part of it is that this, if it were an AP question, it would be very clear that you were using it. Typically in an AP question, typically in an AP question, if it was in part A, then they would say use it for the rest of the problem. But this is not an assignment that was given by College Board. This is an assignment that was given by another teacher, which is why I think that, because normally it would not contradict itself like that if it was AP. Only because this was written by one person, and AP questions are usually written and then proofed by several people. So they usually are not contradictory like that. So we would check the y coordinates and just make sure the relative minimums you can trust because you're going to see that negative to positive change. The absolute minimums you're going to have to trust by comparing the y coordinates with other points. Does that make sense? So you're going to look at every single possible, remember the extreme value theorem, you're going to have a list of your different x coordinates where your critical values are, where your endpoints are, and then you're going to compare your different y coordinates. And I checked my endpoints off to the side because I did it for multiple problems at the same time. And that's how I knew that this was a minimum, is because I had done it over here. We had different information, so we didn't do problems like this. We did other types of problems. Yeah. So we didn't have integrals yet. We just did it in other contexts where you would have been able to find the y coordinate a different way. So we did it when they gave you equations, not graphs to find the area under the curve. Yeah. Yeah. Okay.
How did you know what it was for
G of 7, you'd go up here and you'd find the area under the curve from 0 to 7. So that's why you can see me doing all these markings, as I'm looking at all the areas so that I can add them up. Yeah. So if you wanted, like, that's what you can see all this work down here is I'm saying what all my different y coordinates are so that I can compare them. Yeah. Okay. Any other questions about that? So there's like two things that are going on. There's one where you're just using the original part of the problem to find y coordinates just because this is the notation they gave you. So they're saying, hey, plug in an x value to this notation and just find the y coordinate, find the output. And so you're practicing finding the area under a curve with this notation. And then the second piece of it is, hey, now use the fundamental theorem of calculus to find this notation. And then realize, oh, when I do that, that means that the curve itself is no longer f. The curve itself is actually g prime. So it's been transformed into a whole nother graph, which is an interesting thing, but it's not uncommon to do that. Does that make sense? Yes. So f of t is some random graph they're using, but then because they describe this relationship here, that g of x equals the integral from 0 to x of f of t dt, because of this, and because of what we know about the second fundamental theorem, because of this right here, what they've done is they've written a direct relationship so that g prime of x is actually the same as f of x. So you go over here and you say, oh, f equals g prime. They're actually the exact same thing. It's a notation thing. So, and it's like they've hidden it so that if you don't understand the fundamental theorem of calculus, you would never know they're the same. And then you can't do the problem. But if you understand the fundamental theorem of calculus, then you can go, oh, that's very tricky of you, but I'm smart enough I can figure it out. The thing is, a lot of kids will actually get this problem right because they will ignore, like a lot of you guys, when the problem is in terms of g, you guys all write that it's in terms of f. You guys ignore the variables and are just like f of x, f of x, f of x throughout the whole problem, even though the problem said g or f to begin with or g to begin with or whatever. A lot of students will completely skip over this and they'll just assume it's the same thing. They're like, well, if they gave me the picture, of course it has to do with g. And so a lot of kids will get these problems right anyway. So it only matters, the only time it really matters is if you're doing an FRQ, and this is, you have to do this to get a setup point, and if you don't do it, you won't get the setup point, and if you don't get the setup point, you won't get points for the rest. That's the only time it really matters. So setup point is like in the FRQ, the way that they grade sometimes is that if you don't get the beginning of the problem right, they cancel out the rest of it. And sometimes they give a point for this and sometimes they don't. So sometimes it matters and sometimes it doesn't, but it's good math to say, I understand that this part is necessary. It's not good math for you to end up lucking out and getting the problem right because you didn't notice the variable. That's bad math. So we want to notice that. We want to understand that this is why it's working. So the first fundamental theorem is just the A's and B's. It's just a definite integral. It's just I'm taking the antiderivative. I have numbers there. I'm plugging in the first number. I'm subtracting. I'm plugging in the second number. That's just using integrals, antiderivatives, area under the curve, normal stuff. That's indefinite integral is just antiderivatives with notation, but the fundamental theorem of calculus is when you plug in the numbers.
Oh, okay.
Yeah.
And then this one, the second is always when you have that x.
When you're finding the derivative of something and you have two different variables, you have an x and a t or something with this situation. So maybe what I'll do is maybe tomorrow maybe let's do one of these as a warm-up tomorrow. Should we do that? Okay. So I think what I'll plan on doing is maybe taking number 20 tomorrow, or maybe let's I think, yeah, maybe what we'll do tomorrow is take that FRQ and do that as a warm-up tomorrow. Would that work for you guys? Do the FRQ as a warm-up? It's a pretty typical problem, so it's not a bad idea to try it. So let's do that. Okay, so go ahead and get your notes out from last night. U-Substitution. How did you guys feel about that? It was okay? So U-Substitution is going to open up the rest of integrals for us, just like the chain rule did when we were doing derivatives. That once we learned the chain rule, we could do the rest of derivatives. That's how U-Substitution is for integration. It just makes it so we can do the rest of the problems. So we're going to continue practice. I believe in the notes we did 5 examples. Is that right?
Yeah.
5. Okay, so we're on example 6.
How come it can go in the front? I guess it's imagine that integral like really separates things.
Well, remember how when we would do derivatives, the coefficient would just hang out, and then it'd end up in the front again? Same thing with the integral. Coefficients can just hang out. Yeah. So if they can hang out in one direction and we're doing the inverse, they can hang out in the backwards direction too. Well, if a c is a constant, if you multiply a constant by a number, it's still a constant. So constants, the plus c actually absorb numbers. You can add a number to it, it's still a plus c. You can multiply a number by it, it's still a plus c. It absorbs the numbers until you solve for it, and then it's officially something. Yep. All right, so here is our example number 6. So we've got square root x plus 7 over square root x. The square root x plus 7 on the top is to the 8th power. And we got dx. Oh, this is where this starts getting fun. I just love these so much. These are just so fun. Are you guys feeling the joy in mathematics right now? Are you feeling it? Feeling the joy? Reagan, you're not feeling it? No? Reagan, the hair with the glasses, with the slow shake of your head, it's a vibe. It's a whole vibe. She's like, no. Not feeling it. All right, so where is the inside? Square root x plus 7, so I'm going to say, okay, this is where my u is going to be. Were you confused when I did colors in the notes?
No, when you like rotate, you like how to rotate? How you just squiggle it out? So that's what I did.
Oh. And then you realized it was you. That's funny. That's fine. I support you. Whatever you guys need to do. The boys are like, I do pencil.
I have marker.
Alright, so I'm going to take the u and I'm going to rewrite this as x to the 1/2 plus 7. Alright, so now that we have u, what do we do after that? We find du, the derivative of u, which is? Oh, she already simplified it. Michaela, I had to translate for you. That's too much. That's too much for us. It's 1/2 x to the 1/2. Okay. And then dx. Okay. And then if you rewrite it, what is it? Okay. That's what Michaela said. She said 1/2 root x. She said that in the beginning, and it just threw us all off because we're used to doing it slower. Everybody was like, that's wrong. And I was like, I had to think about it, and I was like, no, that's right. That's right, it just skipped a step. It was too much for us. Okay. All right, so in the problem, we can see the root x on the bottom, and we can see the dx, but we cannot see the 1/2. So what do we need to do? We can multiply the 2 and then multiply the 2. We took the 1/2, brought it to the front. So we took the root x and we rewrote it. And then when we took the derivative, the 1/2 came to the front. Yeah. It's going to still be there. It's going to hang out. Okay, so what we end up having is that we've got a 1/x dx, and so this part right here is the 2 in the du.
So when you're writing this out, are you basically just saving it, like the 1/root x for later when you're plugging things back in?
So what I'm doing is I'm saving. So what this is doing right here is I'm finishing, I'm taking the entire problem and I'm taking the x's out and I'm replacing them all with u. So this is basically saying x and then dx. It's x and the change in x. And so here's u and then du is the change in u. And so this was the rest of the problem. Does that make sense? So now I'm going to rewrite the problem so that I've got everything in terms of u. So I've got the 2, I've got the u to the 8th, and I've got the du. See that? I've got 2, I've got u to the 8th, and I've got du. And most of us, and it kind of depends. Some people are comfortable with keeping the u or the 2 inside. Some people are more comfortable moving the 2 to the front and just not dealing with it. Kind of depends on who you are. So if you guys want to leave the 2 inside, that's fine. If you want to take the 2, move it to the front, that's fine. It's up to you. Both answers are going to give you the correct thing. Okay? So at this point, we are ready to do the antiderivative. So how do we do that? Add 1, divide by, I can move the 2 out, or keep it in. Yeah, it doesn't divide nicely, so the 2 being there or not being there doesn't really matter. So we have 2/9 u to the 9th plus c, and then we're going to take the u out, and what are we going to replace it with? Root x plus 7. Beautiful.
What happened to the du?
It was so when you take the antiderivative, it goes away.
Oh.
So the idea of the du is that we had a volume before, or we had an area before, right? We had a length and a width, so we had units squared. And then when you take the antiderivative of an area, you get just a length. Does that make sense? So we don't have units squared anymore, we just have units. So we just have a line now. Okay. All right, example 7. All right, the integral of sine x times cos x dx. So there's an inside and there's multiplication. Do you guys see it? Sine of sine x times cos x dx. Okay, so what's the inside? Sine x, okay. There's the u. We're going to say u equals sine x. Okay, what's the derivative of u? Cos x dx. Okay, so now we're going to say cos x dx is du. Okay. So when I rewrite this whole problem in terms of u, what's it going to look like? Yeah, sine u du. Okay. So when you integrate sine, what do you get? You used to think you knew these, and now you don't anymore, huh? So if we're picturing the circle, we're going to go counterclockwise. Negative cos u plus c, okay? And so now if we take the u and we plug it back in, what is our final answer? Perfect. Okay, so we're not killing any hedgehogs and we're not killing any what was it, turtles? Is that what you feel if you mix them up?
Wait, there's no integral?
Nope, because we did the antiderivative, right? So when we do the antiderivative, we're done. Whew. My brain is good, I just gotta go a little slow. A little slow.
I just remember when to take the implicit differential. When to do the dx or dy.
So we use U-substitution when there's an inside. So U-substitution is like the chain rule. It's the opposite of the chain rule. So any time that you would have done the chain rule if you were doing the derivative, this is when you use U-substitution. So if you can look at this problem and go, oh, there's an inside, U-substitution. Does that make sense?
Yeah, there's like a lot of moments when we did, like when we did the cone stuff. At one time we had to do like cones, and we did like d of every single variable over dt.
The implicit.
Like the dx over dt versus when you're just doing the derivative and you don't have to add anymore.
So those were related rates problems, and you can kind of tell because they talked about multiple variables and each of them had a rate of change. And so that was like the height had a rate of change in relationship to time, and the volume had a rate of change in relationship to time, and blah, blah, blah. And so the derivative talks about something having an instantaneous rate of change, and they talked about multiple things having that instantaneous rate of change, and that's kind of how you know. Yeah. All right, number 8. All right, this one is going to be sine x times cos of cos x plus 2 dx. Sine x times cos of cos x plus 2. All right, what is u? Cos x plus 2. Okay, so there's the inside. Okay, and then what is the du? Negative sine x dx. So it would go that way for the derivative. Yeah. Oh, sorry. It'd go that way for the derivative. Yeah. Yeah, so there's a sign in the problem, but not a negative. So we're going to divide by -1. So negative du equals sine x dx. Okay. So we're going to get rid of the sine and the dx, and we're going to put a negative du in the problem. Okay. And so what is the integral that we are doing? So it'd be negative cos u du. Okay. All right. So when we integrate this, what do we get? So integral of cos is sine, right? But we've got a negative in the front. We got to drop down. Okay, so what is our answer? Yeah, no hedgehog killing. Okay, this next one is gonna blow minds a little bit. Are you ready? Okay, this one, x square root 2x minus 1 dx. Okay. Okay. So du is 2 dx, but there's not a 2. So we say, okay, get rid of the dx, and then we have 1/2 du. Now, the whole purpose is that we take the problem, we get rid of u's, or we get rid of all the x's, and the whole problem is in terms of u. That's the whole goal, okay? What's the problem? There's still an x in the problem, okay? So what we're going to do is we're going to go off to the side, and we're going to say, okay, the only thing we know is that u equals 2x minus 1. So we have to use this to somehow get rid of that x. Okay? Okay, so what do we do? Okay. Okay. So we got u plus 1 over 2 equals x. Okay, now I'm going to blow your mind a little bit more. I'm going to pull the divide by 2 in front. I'm going to call this 1/2 u plus 1. Are you okay with that? Okay. So we're going to take the x out, and we're going to call that 1/2 u plus 1. Are you guys okay with that? Okay. So now what most people would do is they would take this 1/2 and that 1/2, and they would call it a 1/4 in the front. Is that comfortable? Okay. So we're going to say 1/4 in the front. And then we're going to say we have a u plus 1, and we have a root u, and we have a du. How are your brains? They're okay? All right. I'm going to call this u to the 1/2. Yep, that's exactly what we're going to do. Okay. So u to the 1 times u to the 1/2 is what? U to the 3/2. U to the 3/2, and then what? U to the 1/2. Okay. All right, now how do we do the antiderivative now? Add 1 and divide by it. Okay, so now we can just do our normal antiderivative. So I'm going to keep 1/4 in the front, and I'm going to have u 3/2 plus 1 divided by 5/2. U to the 1/2 plus 1 divided by 3/2. Let's see. How are we feeling? Okay. Uh-huh. Yeah, so we're gonna have 2/5 times 1/4. 2/5 times 1/4. 2/28 is 1/10. Okay, so we're gonna have 1/10. And then we're gonna have 1/4 times 2/3. 1/6. And then we're gonna take the u, and what goes in for the u? 2x minus 1. Okay. Isn't that wild, but kind of cool? I don't know, I low-key love those. I'm like, oh my gosh, those are so neat. Yeah. Yeah, if you want to blow your parents' minds, just show them that problem. If we want to make the kids below us cry, we should just do that problem on the whiteboard and leave it.
Yeah. Make it really big.
Uh-huh. At my old school, I used to do that all the time. We used to do that, do all the problems on the whiteboard and just leave them. Okay, your brains are doing okay? They're toasted. Okay. I think we're gonna leave it there. All right, so the assignment for today. Larson.
Yesterday was
Oh,
I can't go to the so even
I already heard.
She's aching. Oh, this way. How old
I
are
thought
your
it
headaches?
Um, they're not quite as bad.
But they're still happening?
Yeah. We're going for a world record. But I was getting migraines like real bad last year. And my